Okay. So welcome everybody. First of this series that we're starting up, um, and for the Space at VT Center here at Virginia Tech. I'll talk. I guess I'll introduce first our director is Dr. Scott Bailey, who's been with the center I think somewhat from the beginning. As many of us as it started coalesce, we have added some here and there, but I'll try not to take too much and let you kind of introduce the center and talk about our research in general.
Okay. Should I do that now?
Yeah, go ahead. Yep.
All right. Well, thanks to all of you for being here and joining in this seminar series. It's something very important to us. We are the Center for Space Science and Engineering Research, Space at VT, we call ourselves. Primarily, our faculty are in the departments of electrical engineering and aerospace engineering, but also mechanical engineering, and we're expanding out. We have some new members from different departments, including physics and geosciences. We want to reach out because there's a commonality to all of us who are members of Space at VT in that, we do research related to space, either from space or about the space environment or space technologies. And so there's those common themes, technologies that we all use. There's some relationships, there's curriculum interests that we might have for our students that overlap. And so we're trying to expand in that sense so that we can all be talking about those commonalities. And this seminar series is a big part of that. Most importantly, when we talk about our outreach, it's to students, right? Most of you on this Zoom meeting are students. And one question the university should always be asking the students is, how can we better serve you? And so we have interest in space science and space technologies, and you have interest in space science and space technologies. And, how can we better connect you to our research and the things we're doing, get you involved, connect you with our industry partners so that there are jobs for later, talk to you about graduate school for those of you who might be interested in. Whatever you're interested in, how can we better work with you and talk to you? That's a key component to our center, and why we're trying to do more that's sort of external, bringing in people from different areas of the university, talking to students more through the seminar series, genuinely trying to involve you in this seminar series. And Kevin's going to talk about that. We really want you to participate, both listening and giving talks, and we're going to reward you for that. And we welcome any input you have on that process. When we say space science and space technologies, it spans the gap. We have people who study the Earth's upper atmosphere, people who look at the Earth's surface and lower parts of the atmosphere, but from space using space technologies. We have people who look outward. We have people who develop technologies to do that sort of thing, the remote sensing, or maybe the spacecraft itself, or interesting orbits that make all this work, certain materials that are important, and all kinds of other things that relate to it. We're very diverse inside our center, but again, the commonality is space, and an important commonality is that we all work with students, and this seminar series is very much about that. So I'm really hoping today and every talk we have for the rest of the year and permanently, we hear from you how better we could provide talks that you're interested in, how better we could involve you, how better we could answer your questions. That's really what it's all about. So please use this as your time to learn what the university has to offer with regards to space and help us evolve it to better serve you. Maybe before going back to Kevin, if anybody has any quick questions, I want to get to the seminar itself, but if you have questions now, please ask. Okay. And always, you can email any of us at any time to ask any questions you want to ask. So, Kevin, back to you.
Yeah, that sounds good. Thanks, Scott. Thanks, Dr. Bailey. I did want to. I've been sharing here our website, which has some information on that. I'll mostly point you to a couple of things here. Part of it is our the seminar series itself, if you want information on that, and some of the kind of words that I'll kind of go over and try not to read straight from this. That's one thing that Dr. Bailey kind of alluded to, is that we've been fortunate enough to come across some funds where we want to actually award the students, whether it's a student individual or a design team that makes a presentation in here, between this semester and into the spring semester. At the end of the spring semester, the Space VT faculty will pick the two that are best, one in engineering and one in space science, that are the best kind of presentations or seminars that we've seen, and award up to $2,500 to take that research and either go on to present it at a relevant conference, or to any kind of research expenditure, whether you need like a little bit of hardware or something to spend with that. So that's what I said. That's the extra motivation for our students here to present. But we will be hearing somewhat, as we did last week, from faculty. We certainly will encourage that from time to time. And two, sorry for last week, it was a little bit confusing. It just so happened the time that we're doing a little bit of a joint seminar with some colleagues that are at the University of New Hampshire, as well as at Johns Hopkins. So we heard from a faculty or a research colleague, I should say, from Johns Hopkins there last week. Otherwise, too, if this is, everybody should receive this because you're on the center mailing list, and then a calendar that'll list kind of another place that you can find the information that we're at. While I do have kind of the floor for a little bit, I did want to introduce some things that we've been doing for social media here. One of them is on LinkedIn. So you can follow us, and from time to time, we'll be posting some information about that, and certainly about these seminars and links to those. And you can see one thing that is a little bit new for all of us in the times of all these changes is that we have been moving facilities some. So some of the faculty are a little bit maybe discombobulated or a little bit kind of stretched here because we're in the process of doing a lot of moving. But hopefully, as the weeks in the upcoming weeks, we're able to kind of get our better footing. So I guess just as a general thing these days, but be a little bit patient maybe if you're trying to reach out to faculty and try to get a hold of them. And otherwise, too, we have a YouTube channel that's not super busy. Part of this was from a lot of the shutdown that we had and kind of reduced operations with related to the COVID response. But we are hoping to put more content up here. So feel free to subscribe and follow along the videos that are being populated there. Any quick questions about the seminar, or any kind of just general questions of that nature? Yeah, it's hard for me to find the mute button, and sometimes hard for me to click it there. We are encouraging or soliciting people upcoming. These ones where it's just seminar series, these are open slots. So if you have some research that you would like to present, or some kind of thing that's related, it doesn't have to necessarily, research can be kind of a scary word. It's something that is a topic that you're interested in or have learned something about. Then feel free to contact me. We can put it together in a presentation and present it here. So I think without that, I think I'll stop sharing and we'll turn it over to our first presenter, which is Dr. Karlton. I'm going to butcher the last name here. Wirsing?
That's correct, Wirsing.
Okay. The title of Multifractal Analysis of Space Weather Data. And I'll leave you to it. Feel free to, I think you should be able to grab the screen and share it, and we'll hear from you.
Wait a minute. Let's see. Where's share screen? Oh, here
Uh,
it is.
yeah.
Oh, yeah, I got it. You see it?
Yep, got it.
Okay. My name is Karlton Wirsing, and my research topic is multifractal analysis of space weather data. I recently completed my dissertation back in May. My first master's degree was from Virginia Tech in computer science, and I got a second one in electrical engineering. Then I went on to get a PhD in electrical engineering. Wait a minute. How do you advance slide in PowerPoint? It's not letting me do that. Oh, there we go. Okay. Space weather causes. Wait a minute. This isn't working. Yeah, I'm having a little problems with PowerPoints because it's a dual screen and one screen's advancing, the other screen isn't.
Gotcha.
All right, let me change this.
Okay.
Okay, now we got it. Sorry about that. Space weather causes effects to infrastructure such as power systems and pipeline. The signals are often irregular, so the problem is accurate analysis of them. So the topic is to analyze data sets of geomagnetic induced currents for multifractal behavior, specifically ones relating to a pipeline network in Finland. Our findings were that there's a consistent multifractal nature to the GIC data, and we also found that the apex of the singularity spectrum shifts as the overall disturbance of the magnetosphere increases. What we found was that the sun seems to be driving the system towards greater amounts of order, which was interesting. Although there's considerable variance with that, as you'll see in the following slides. And sometimes for some of the storm functions, some of the storm, the signal analyzed split into two different monofractals at different levels, which is also interesting and needs to be analyzed further. This is a diagram of the heliosphere. Currently, the heliopause extends beyond the orbit of Pluto. However, this was not always the case. In the sun's 230 million year orbit around the Milky Way, it goes through clouds of varying density that can push the heliopause to within Earth's orbit, at which point Earth is more affected by the interstellar weather than space weather. This has been hypothesized to be linked to several ice ages in Earth's past. It also shows that effects on the Earth can extend from beyond the solar system. This is a diagram of the magnetosphere. The magnetosphere carves out a section in the heliosphere that repels the sun's magnetized plasma. That's a solar wind. This has been likened to a ballerina skirt, as the image on the right shows. As the sun rotates, the rotation carries with it the sun's magnetic field. Beyond the interactions with the solar wind, there's two different extreme solar events that occur. They're called coronal mass ejections and solar flares. Coronal mass ejections consist of large releases of magnetized plasma, and solar flares consist of large releases of electromagnetic energy. Solar flares were detected first since they're optically visible, and they're easily optically visible, and they're originally thought to be the cause of space weather, although and of coronal mass ejections, although now they're determined to be a secondary cause, and the primary drivers of space weather storms is coronal mass ejections. They also affect the Earth differently solar flares affects primarily the ionosphere, and coronal mass ejections primarily impact the magnetosphere, which can create secondary disturbances as it trickles down to the ground, creating a long chain of events starting with the sun and ending with Earth. As mentioned earlier, the effects of space weather includes geomagnetic-induced currents in power systems. That's been linked to several blackouts. Geomagnetic-induced current for pipeline corrosion. It's interfered with railroad networks in Russia. The particles sometimes cause problems with satellites, and it also causes problems with the ionosphere, including changes in radio propagation, which can affect GPS navigation. Also, during 1979, heating of the ionosphere due to the solar maximum at the time caused the early re-entry of the Skylab space station. NASA models projected that it would re-enter approximately 3 years later, which created the possibility of a shuttle mission to boost its orbit, but that turned out not to be possible. And it re-entered over the Indian Ocean and crashed into the outback of Australia. This is a diagram that represents the information on the preceding slide. You guys have probably seen this image before, showing the different effects of space weather on different terrestrial technological systems. The effect on power systems is that it induces a quasi-DC current on the power network. GIC is extremely low frequency and is picked up by long conductors that act as antennas, specifically power lines and pipelines and the railroad networks as mentioned earlier. What this causes the power systems is it causes a half-cycle saturation in power transformers. Basically, the quasi-DC current shifts the alternating current waveform into the saturation region of the transformer, which can lead to thermal failure of the transformer, increases in reactive power. This is primarily due to the fact that transformers, for cost efficiency, are kept in the near efficient operating range, so any deviation can damage them. The costs include transformer replacement and loss of revenue from system downtime. Transformers themselves are several $1 million, so replacing them is expensive, and loss of revenue from industrial and other users can be astronomical. It shows the graph. The graph shows the effect on the effect of GIC on AC signals. As you can see, the red area is the saturation region, as the GIC alters the alternating current waveform. It can also cause corrosion and bury pipelines. 1 amp of current for 1 year can cause the loss of 10 grams of steel in the pipeline due to the following equation, as indicated on the slide. One way to mitigate this is to maintain a small current from Earth to the pipeline to counteract this, usually on the order of about between 800 and 1100 milliamps. Now, the impacts on the terrestrial system can vary due to the intensity of solar storm activity, whether and where the massive particles ejected during a solar storm strikes Earth, the facility's geography, its proximity to the poles, and local geology, such as the conductivity of the soil, the length and connection of the lines and winding connection of the connected transformers, as well as for a pipeline, the equivalent placement, and the design of the connected transformers and their power loading during the GMT. In addition, since the sun's magnetic field reverses every solar cycle, it can also vary depending on whether the solar magnetic field is in similar to Earth's orientation or opposite to it, because of opposites attract and same charges repel. There are various organizations and working groups related to space weather, including the IEEE Power Systems Relay and Control Committee, the Space Weather Operations Research and Mitigation Group for the Department of Energy, the United Nations Office for Outer Space Affairs, the Space Weather Prediction Center of NOAA, NASA's Living with the Star, and the Space Weather Service Network of the European Space Agency. In order to accurately measure the impact of a solar storm, we need to measure various aspects of Earth's magnetic field. So that we use magnetic observatories around the Earth to measure changes in the horizontal component of Earth's magnetic field. And readings from these are used to calculate the following indices: the AA index, the KP index, which gives an overall state of the magnetosphere, the DSD index, which measures the equatorial rain current, and the auroral indices, which measures the indices in the northern hemisphere polar regions. The various observatory locations are shown here. As you can see, the ones for the auroral indices are at the top of the map near the North Pole. The KP index are at more mid-latitude regions, and the DSC index are more near the equator. There's no comparable network of magnetospheres on the southern hemisphere because most of the area is either Antarctica or ocean. From the historical AA index, we can see trends in space weather. GIC was considered a nuisance to utilities up until the blackout in Quebec of 1989 that knocked out a hydro station for about 9 hours. Then it was determined to be a significant threat. There's also, as we're going through a increasing amount of solar weather, one paper in 1995 showed this trend. However, I extended the trend beyond that to current data, and it seems to show that we're entering into some sort of lull period. We have to wait until several solar cycles occur to see whether this is just a temporary trend or whether we're actually in a permanent lull period from this. This shows the KP index for 2003 with the Halloween storm of October 31st shown here. That was one of the most significant geomagnetic storms, and that it even caused auroras as far south as Maryland. This provides an overall state of the magnetosphere, and its values are from the 13 observatories indicated on the location slide. You show the relative values here. Anything from 0 to 3 is basically considered a quiet period. Starting with 4, we get into active, and storms usually occur from 5 through 9. With the Halloween storm being about at 9. This shows the DSC index for 2003, which gives an overall state of the equatorial rain current, which is computed from values in the 4 observatories on the location slide. The Halloween storm shows a significant weakening of the rain current, which is typical during a solar storm, but you can see just how much the rain current decreased here. On the diagram on the right, you can see a diagram of how the rain current goes around the equator, as well as various other currents in the magnetosphere. The AA index provides an estimation of the strength of the auroral electric jet index. It consists of the difference between the upper and lower values from the 12 observatories in the northern polar regions. The AU index is the upper value, and the AL index is the lower value, and the AO index is the midpoint between them. It shows considerable more. It's a considerably more noisy index than the DSC index, as you can see in this graph. Getting on to the topic of the paper, different papers have different definitions for what a fractal is. Generally, the properties of a fractal are replicated across several scales, and they're regular in some manner to exclude trivial cases such as straight lines. Benoît Mandelbrot showed that regular data sets can have simple mathematical definitions. However, these shapes were known throughout times. They're often called, I guess, monster shapes because they had no, they're completely undifferentiable and didn't conform to typical mathematics. Here are some examples of fractal signals. As we're familiar with ideal white noise in that it shows a slope of 0 on a log-log scale. Red noise is the integration of white noise and shows a slope of -2 on a log-log scale. And pink noise occurs frequently in background radiation and also is what basically the power spectrum of what music is and shows a slope of -1 on a log-log scale. These shows how frequencies at the lower band are related to frequencies at the upper band. And red noise is so named because its noise is shifted more towards the red part of the spectrum. It's also basically, it's also referred to as Brownian motion. Multifractals are defined as fractals intertwined with fractals. Instead of having a single dimension, they have a spectral dimension, a spectrum of dimensions. Brownian motion shown here is shown at a single point at the polar exponent of 0.5. Whereas for a multifractal, most the points concentrate at the apex of the parabola, but it extends to either side with different points corresponding to different polar exponents. Fractals and multifractals have many natural occurrences, such as coastlines, mountains, clouds, areolar lungs, distribution of galaxies, cosmic ray particles, craters, heartbeat, turbulence, and sunspot numbers, as well as artificial examples such as music, art, antennas, stock market data, distribution of people across the US, and artificially generated landscapes, such as ones generated for movies and all. One example, if you watch the movie Hunting the Hidden Dimension, is that they found that blood tumors, the distribution of blood vessels in tumors had a lower fractal dimension than that of normal tissue, showing a more chaotic distribution, which is kind of interesting. In order to analyze this, we're using the wavelet transform. Characteristics that wavelets share with the Fourier transform are orthonormal bases that allow for simple formula for coefficients, algebraic relations that allow for fast transforms, and complete bases that allow approximation standing accuracy. Differences between the wavelet transform and the Fourier transform: that wavelets have compact support, but Fourier series do not. Fourier series extends throughout the entire signal, whereas wavelets decrease to 0 after a certain time. In discrete wavelets have vanishing moments that suppress polynomial trends, which are useful in economics to suppress trends in data for analysis. These are the various equations for the wavelet transform. The wavelet transform itself is an integration transform that consists of integrating the function multiplied by the complex conjugate of the wavelet if the wavelet's real value, solely real valued and not complex valued, then this doesn't have any effect. It would just be the same as if it was a non-conjugate. The wavelet itself is shifted in time and scale by with A being the scale and B being the time. And properties of the wavelet functions are that it must have finite energy, which is the immiscibility condition. It has a 0 DC component, and its overall integration is 0, so it oscillates like a wave. Discrete wavelets have additional properties. The first equation is the vanishing moments, as indicated earlier, that will suppress any polynomial up to or including polynomial degree k. It also has a companion scaling function with whose DC component is 1 when And the scaling function must be orthonormal to the wavelet function, that their integration must be 0. In addition, this shows that in the frequency domain, the frequency response, the two functions are symmetric around pi over 2 radians. The scaling function must have a DC component so that the wavelet transform can terminate in a finite series of steps and be invertible. Basically, what this looks like is that it, as the following slide shows, it shows the discrete wavelet transform that's basically a pyramid transform with that creates an output of levels of detail coefficients here shown as W and one level of coarse coefficients, which shows as V. What this looks like is basically a low pass filter. It's basically a high pass filter, a series of band pass filters, and a low pass filter. Usually this is implemented as a finite impulse response filter with scaling coefficients shown here. And the wavelet coefficients will be the scaling coefficients in reverse order with every other one multiplied by -1. After each step, for discrete wavelet transform, the half the values are eliminated in a decimation step, which enables the output to have the same number of coefficients as the input. However, this step does not have to occur for the stationary or discrete or the undecimated wavelet transform. There is no decimation step, so basically the number of coefficients are each the same as the input level, and so the total number would be the number of coefficients at the input level times log base 2 of the number of coefficients of the input. In my master's thesis, I found that this creates this gives you advantages for noise filtering sometimes about 9 decibels. To estimate the singularity spectrum, there are several different methods. One is the wavelet transform modulus maxima using the continuous wavelet transform. One is the wavelet leader method that we used. Other is using wavelet coefficients, multifractal determinate fluctuation analysis in rank order. The best method we found is the wavelet leader, which we use with multifractal determinate fluctuation analysis for verification. For the wavelet leader, it requires less computation than the wavelet transform modulus maxima. It handles full multifractal spectrum, handles both custom and oscillating singularities. When combined with the bootstrap method, it can be used to estimate confidence intervals and perform statistical hypothesis testing. And also has automated range selection, allows us to analyze the best fit over several ranges. What the bootstrap method is that it was created by Bradley Efron in 1979 and is one of the, and with the introduction of computers, it's been helpful for signal processing. The problem is we have only one instance of the data set, so the method works by randomly resampling a given data set with replacement. With the wavelet leader method, since the wavelets have since wavelet coefficients have a short-term correlation, that has to be maintained. The bootstrap can be used to estimate the confidence intervals and used for statistical hypothesis testing. We use it with a cumulant method with accumulants to indicate whether something was a fractal or multifractal or not. Wavelet layer method is used to analyze multifractal behavior over levels of the wavelet transform. Fractal and multifractal behavior typically do not exist for all ranges for naturally occurring fractals. Mandelbrot himself illustrated this by, if you look at Britain from a far enough distance, it looks like a single point. And if from a close enough difference, it would look like all the empty space of interatomic space. You have to select the ranges as to which the fractal occurs. Now, for mathematical fractals, they do occur over all ranges, but that's the ideal case. So the user needs to select the ranges over which multifractal and fractal behavior occur. Usually this is done visually by selecting ranges that have a straight line on a log-log plot. The problem is this can be error-prone and error-efficient for bulk analysis because the person would have to analyze each individual data set, and for our case, we had 257 of them. since we're sorting out by day. So the key is to select a metric that indicates a good fit, and to either maximize or minimize that measurement. The measurement selected consists of the sum of the residuals from the fit or the line over the cumulant and the Q values. And this can, and then we can look at which ranges have the best fit, and either automatically select one or select one manually. The surrogate analysis allows us to verify that the multifractality is independent of the characteristics of the signal. So we use two different surrogate data analysis techniques, Shuffle and the IAFT. Shuffle allows us to verify that the characteristics are independent of the amplitude of the signal, and the IAFT, or iterated adjustive amplitude Fourier transform, allows us to verify the characteristics are independent of the Fourier power spectrum of the signal. Now, bootstrapping allows us to verify multifractality with one method, but it was suggested to us by a reviewer of the paper that the use of another method allows us to provide additional confirmation. The problem is that different methods can produce different results for the same synthetic signal. So we use multifractal determinative fluctuation analysis, since the implementation produces a similarity spectrum similar to that of the wavelet leader method. For our for the data, we use a data set provided to us of the geomagnetic induced current in pipelines in Finland in 2003. Of those, we had 257 complete days, so we're analyzing them day by day. From those, we found that using automated range selection, 3 of them had no classification, 80 of them had monofractal classification, or 31%. 174 of them had a multifractal classification, or 67%. For automated range selection, it found that 66.53% were that ranges 3 and 4 had the best selection, the tightest fit, but sometimes longer ones did occur. We also analyzed by KP index and split the data up into 3-hour intervals. From the KP index, we found that for 2003, 50% of the KP values are either 2 or 3, showing low activity. However, there were about very few, such as 3 for the Halloween storm, that showed a very high activity. And it shows that it's sort of approximate bell shape with a long edge with a long tail at the end. When we analyzed the cumulants by KP index with 3-hour values, it seemed the first cumulant, or the apex, seemed to show the median showed a clear trend upwards, which would seem that the sun is driving. When the sun becomes more active, it seems to drive the system towards more order. The other cumulants were flat. So for this data set, really only cumulant 1 showed a significant deviation from 0. All the others seem to be distributed around 0. This shows the data for one signal. It's a relatively quiet state. However, since the median KP index is around 3, which is quiet, which is indicated as quiet, and so basically the median for 2003. However, the maximum current on the pipeline was 0.67 amps, and the minimum current was negative 1.08 amps, which is still which is still a lot. From this, we see the cumulant values. The apex of the similarity spectrum is at 0.45. The bootstrap rejected these being equal to 0 for this one, for C1, C2, and C5, which indicates that's multifractal. Multifractal is defined as any one of the C2, C3, C4, C5 is not equal to 0. If it's strictly monofractal, then only C1 would be equal to 0, and if it's a no classification, then then all these would be not rejected. Actually, only C1 would not be equal to 0 for a monofractal. The values here, the values in the preceding graph basically corresponds to the slope of the lines on the cumulant graphs. You can see the relative tightness of fit here and here. There are some more deviations at the higher level cumulants. I mean, at C1 and C2 has a relatively tight fit, and the C3, C4, and C5 have a sort of a less tight fit. From this, we can calculate the scaling exponents in the singularity spectrum for levels 2 through 6. You can see that the apex of the singularity spectrum is 0.45, with the positive Q values are the green are the blue is the blue part of the graph, and the negative Q values are the green part of the graph. So on the singularity spectrum, it shows the more truncated values for more truncated for the negative Q values, with which corresponds to the smaller fluctuations in the singularity spectrum, and the positive Q values correspond to the larger fluctuations. For surrogate analysis, we see clear differences in the surrogate singularity spectrum for the median for shuffled and IFT versus the original. And the MFDFA shows similarities between for the singularity spectrum. For the positive Q values, the negative Q values that it didn't compute correctly, which corresponds approximately to the singularity spectrum from here to about here. From here, from 0 to about 0.75 here, which doesn't capture the rest of it, so that needs to be analyzed further. But it did match up pretty cleanly from 0.45 from a 1 on DH to a 0.75. The goal of this research is mitigation procedures, so that infrastructure can be used during a geomagnetic storm. Mitigation consists of either active or passive procedures. Active consists of creating a countercurrent through the pipeline or transformer to nullify the GIC. Passive procedures consist of the use of devices such as transformer design, capacitors, or high resistance to ground. That usually only corresponds to power networks. Really, the only counter you can do with a pipeline is active. So transformer designs for power systems in common use range from least affected by GIC and most affected are three-phase core form, three-leg core, three-phase core form, five-leg core, three-phase shell form, conventional core, three-phase shell form, seven-leg core, single-phase shell form, or core form. Now, of course, the obvious question is, why doesn't everybody use just a three-phase core form, three-leg core, if that's the most resistant one? And the issue is that the issue is, of course, existing infrastructure, and certain systems may require other ones due to either size constraints or cost constraints. From what we found is that most of the GIC signals analyzed were multifractal in nature. We hypothesized the multifractal signature of the GIC signals indicate an origin from space weather. This is useful for modeling purposes, both for prediction and countermeasures. So for future work, we need to do further analysis of applications and mitigation procedures for critical infrastructure, including power lines, to active countermeasures, prediction of future values with past values, such that if we know these the values of the point in time from such and such time in the past to now. If we know the multifractal signature, then maybe we can predict what the future values will be and create a countercurrent to counteract that. We also need to analyze data set for connections to chaos theory and strange attractors for prediction purposes as well. Explore how the multifractal spectrum varies across multiple years of the sunspot cycle and by location. And so, as I mentioned earlier, the sun reverses polarity every 11 years, so it needs to be done. It needs to be analyzed over at least 22 years, since the orientation of the sun's magnetic field has an impact on how it interacts with Earth's magnetic field. They explore correlations between terrestrial observations and space-based observations. Currently, we've been only doing terrestrial observations. This can show how the signal changes as it progresses through the magnetosphere. We need to explore possible changes in dimension calculation by vanishing moment, although for the signals analyzed, anything above 3 seems to have similar dimension calculations. Currently only the wavelet leader has the bootstrap method and automated range selection analysis applied. What we need to do is also apply it to the other multifractal analysis techniques such as MFDFA and rank order method. And so we can do a full comparison of all of them. Also the use of a sliding window. So since we're currently looking at the data set day by day, use of the sliding window will show us how the multifractal spectrum changes during the day, as well as when the storm sets and then the recovery period and all that. Also, the use of Ito or stochastic calculus and fractional calculus for modeling. I read that Ito calculus is frequently used in economics, and I was for bounding motion and fractal analysis, and I was wondering if it can be applied to our data set for space weather as well. Also need to look at automated joint multifractal analysis, such as between multiple different locations, including space-based and terrestrial. The ultimate goal is, of course, to develop a numerical space weather prediction similar to how we have terrestrial weather prediction. Currently, we're about 100 years behind, and one of the problems behind terrestrial weather prediction, and one of the problems is that we're dealing with a lot larger space, a distance to analyze, and a lot less sensor data resolution. Now, Lorentz created these differential equations in the 60s, and this is called, of course, the butterfly effect. This was basically the path a particle may take if a cylinder horizontally is being heated from the bottom and cooling from the top. This is how a cylinder of air would behave, and it has clear order in that it orbits around 2 different points. However, for certain parameters, it is considered chaotic. And I was wondering if this can be applied to our space weather calculations as well for analysis. So, any questions?
I guess this is the usual. It's still new to me. If this would be the applause, certainly. Thank you, Dr. Wirsing, for presenting that here. And yeah, anyone out there, this is time for if you don't have a microphone, feel free to use the chat feature here on Zoom and pass along any questions. Thank you for your presentation here today.
Well, if there are no questions, it's understandable. It's kind of a complicated topic to deal with.
I might start with one here, and wondering what's the I guess what was the motivation? Might kind of be a simple one. What was the motivation or kind of reasoning for looking at, there's a lot of, I think, ways that people here, some of the grad students or professors have looked at, waves and things like that. But I was wondering what was the motivation for looking at it with, and maybe this is, I just see Sherling's question coming in relating to GIC data. What was the motivation for using that GIC data for your analysis here?
Well, my advisor, Dr. Milley, was talking to some people from, he's talking at a conference with a person from NASA, and they were wondering if we could analyze some data for them. So we did. We're looking for, I also have pulsar data sets on my computer from the Arecibo Observatory in Puerto Rico that I need to analyze sometime too, because I was wondering if we could also analyze multifractal signals for them, and that's across several light years too. So this fits with my interest in space as well as fractals and multifractals. And I also, when I first started my master's thesis, I didn't know anything about the wavelet transform, so that's why I did my thesis on. So since my background is originally computer science, I can write a lot of the software myself too. So it kind of all folds together. Although we did use, for the wavelet leader method with Bootstrap, we used we took a MATLAB package from off the internet from a paper I referenced in my dissertation, then I heavily modified it and added a bunch of features to it.
Okay.
It came with the Bootstrap method, but then I added like surrogate analysis. I added a lot of other stuff to it, and I even made it print up a nice report of everything when I analyzed the data set.
Yeah, it sounds very interesting here. To relay Sherling's question, how difficult would it be to obtain the similar? Because I did notice that it was GIC data in Finland. How do you know of anywhere that you'd be able to attain that somewhere here in the U.S.?
Well, the observatory data themselves, that's freely available. The DST index and the AO index and all that, you can download that off the internet. That's what I did. The Finland data was provided to us, but we don't have permission to show that. Now, of course, there's like a lot of other data sets off the internet, especially from government-owned space satellites, because those are considered public domain since we're taxpayers and we pay for them.
Yeah, I guess it's more focused on the. I guess, have you been able to, or had you thought of looking at acquiring ground-induced current data from a power company here in the U.S. instead of only looking at Finland? Because I think the maybe follow-up question to that is that there's we know of a lot more maybe instruments in a wider kind of spatial area in the U.S. rather than in Finland.
Right. Well, what makes Finland interesting is that it's so close to the pole, so the effect is, of course, amplified. But I did attend a class in space weather down in Texas, and they're looking at that as well. Now, the other interesting thing I found about my research is if you go to the southern hemisphere, most populous city down there is, of course, Cape Town, which is, if you put it on a map of the northern hemisphere, it would occur about the latitude of Atlanta. So there's not a lot of developed infrastructure that would be affected by space weather down there. There's no long networks of conductors in Antarctica. They just basically have small scale generators. Usually the large conductors act as huge antennas that can basically receive the low frequency signals from the GIC. Since they have very long wavelengths.
That sounds good. Yeah. Any other questions here?
We're possibly looking at talking to Dominion, but The other problem is power companies also like to keep this data proprietary. But you can probably find data sets for scientific research satellites.
Yeah, certainly understand that is one kind of tricky thing with the US is a lot of the power companies are private and they keep that as a proprietary information. So, but yeah, we do want to keep it to roughly an hour, but it doesn't have to stop here at just an hour. But if anybody else has any other questions, feel free here to either say in the chat or passing them along through voice.
Currently, I'm working with my advisor and some groups in Tanzania to also apply the multifractal technique to EEG data, since it's also chaotic, seems to be chaotic in origin. So there's lots of variety.
Well, sounds good. I guess with that, not hearing any other questions here. Again, thank you very much, Dr. Wirsing, and for presenting that. And before we all go and kind of end here, I did want to reiterate that we are still looking for a presenter for 2 weeks from now. We'll have our next one on, let me pull it up here real quick, September 30th, the last day of this month. At the same time here at 2 p.m. On that Wednesday. So if you're interested in presenting any kind of amount of to work at kind of any kind of range, anything that relates to space, it could be about rockets, it could be about planets, it could be a similar thing about signal analysis, as we've seen some here. Anything that kind of relates to space, it doesn't have to be as much kind of deep and focused on into it. But feel free to email myself here, and I think you should be able to find my email address on the seminar series website. So.
I'm happy. I was happy to be able to get the ball rolling. Sometimes it's hard to go first. Yeah,
certainly. Thank you. That was a very good. You kind of contacted me very, very quickly after that first call. So yeah. Otherwise, thanks everybody for joining, and we'll see or talk to everybody here in another 2 weeks. I would say, yeah, for a couple of questions coming in, if I can get the posting and the video working right, hopefully this will be posted to YouTube here in the next, I was going to say 24 hours because I have a few things to do this afternoon. But otherwise, yeah, thanks so much.